Okay, so good afternoon. So we will continue with where we left last time, and we were discussing optimization problems, and these are the general form of the optimization problem, where you have the objective function and then the inequalities and the equalities and so on. Okay, so in this case there are m inequalities and then there are p equalities, and yeah, so this is what I've defined last time. And here x is called an optimization variable or decision variable. F naught is called objective function, and then fi's are called inequality constraint functions, and hi's are called equality constraint functions. And then if there are no constraint, this means that m is equal to p equals to 0. Okay, so in that case, these things will go away, and then we will call it a unconstrained problem. The domain of the optimization problem is the intersection of the domain of these all the functions involved here. So objective functions, inequality constraint functions, and equality constraint functions. So here objective function is also included. So f naught is also there. So they have to have the value domain. A point x is called feasible if it satisfies these inequality and equality constraints. The optimization problem is called feasible if there is at least one feasible point. And then we can collect set of all feasible points and call it a feasible set or constraint set. And then the optimal value is the minimum value taken by the function if it's possible. So we take the minimum of that. So it's like infimum. So minimum may not exist, but infimum will exist. So, and then provided that x also satisfies the inequality and equality constraints, p star is allowed to take positive and negative infinity values. Problem is called infeasible when p star is infinity. Well, when p star is infinity, this means that we are taking infimum of an empty set. Okay, so that means that this is, in that case, it's infinity. In other words, there are no feasible set at all. Okay, so in that case, it will be infeasible. Problem is unbounded below if there is a sequence of points xk for which the objective function tends to minus infinity as k tends to infinity. And then we define so-called locally optimal problem. So x star is called optimal if it solves the given optimization problem. In other words, x has to be, first of all, it has to be feasible, and then it has to attain the optimal value. Okay, in other words, x star must be equal to p star. Optimal set is the set of all optimal points. In other words, there will be cases where you may not have a unique optimal point, but you may have many points for which the same minima is achieved. So in that case, we will get a set of points. If there exists an optimal point, then we say that the optimal value is achieved and the problem is solvable. In that case, we say declare that the problem is solvable. If the optimal set is empty, then we say that the optimal value is not attained. Okay, so optimal value is never attained. So optimization problem is the same thing like we did before, but now we are describing epsilon optimal point. So often when you do iterative method, use iterative method to solve convex optimization problem, then you can only attain optimal value up to certain precision. In this case, it's like you are close to the p star by up to epsilon value. Okay, so this is the definition of epsilon suboptimal. So x bar is epsilon suboptimal if it is epsilon distance away from the p star. Okay, and then the set of all x bars for which fx bar is within epsilon distance from p star. Okay, then we call it so then we call this a, since we are always minimizing, so we only worry about this interval. Okay, so this is the epsilon. So all the points here will be in the epsilon suboptimal set. Active constraints. So we have described active constraint. This is something we will come back to later on. For the moment, active constraint means that if x is feasible, and then the ith constraint inequality constraint, if it becomes equality, if the ith inequality, so in this case here, if the ith inequality becomes equality for some x, then we say that the ith constraint is active now, or the ith inequality is active. Okay, so then we call that constraint become active. Okay, inactive constraints are if x is feasible and fix is less than 0, strictly less than 0. So this inequality can be either strictly less than 0 or it can be equal. So if it satisfies equality, then we say that the inequality, this constraint is now active. And if it satisfies strict inequality, then we say that that constraint is inactive. Redundant constraints. A constraint is redundant if by removing this doesn't change the feasible set. Okay, so there may be some redundant constraint. Removing that will not change the feasible set. So we can define feasible set using some compact notation omega. So this is the set of all points that satisfies inequality as well as the equality constraints. So we can use the shorthand notation like this, and then we can write it in a very short form. Minimize f of x subject to x belongs to omega. In other words, x satisfies this inequality. So here omega is the feasible set. So we can write this more compact form. And then we have seen some examples of when we have the feasible sets, what is the optimal value and when this optimal value is achieved for 3 examples. And we have seen graphically what are the cases we have, like when the optimal point exists and it's unique. That's the first case. And then in the second case here we see that the optimal point does not exist because this guy keeps going down. So you have to keep going there. So it will achieve at minus infinity. So in that case, we say that it doesn't exist because infinity is not a valid number. So and then we have seen cases where we may have multiple of the optimal points. Okay, because there are 2 points for which the same minima is achieved. So we can have an optimal set with more than 1 elements. Okay, and we may also have a case where x star again does not exist. For example, in this case, it's a unconstrained optimization problem because we have taken all of x. Okay, these are constrained because we are putting some bound here. We are putting some bound, and here also we are putting some upper bound. So these are the graphical examples of what are the cases where we have optimality and how many and so on. So we keep writing this standard form. Okay, so now, I mean, so far we have written is like, we have not talked about standard form, but now what we want to stress on is the so-called standard form. In standard form, what we have to be careful about is the following. The right-hand side of the inequality and equality constraint are 0. So we have to make sure that these guys are right-hand side is always 0. Right-hand side of equality as well as inequality should be always 0. So for instance, if someone gives me an equality constraint like this, then I should form hi to be, I put gi tilde on the right hand side. So gix minus gi tilde x. So I redefine a function hi like this, and now this is equal to 0 I can write. So we may have to do this to bring this in the standard form, and only less than equal to is allowed. Okay, so only less than equal to is allowed in standard form. So we have seen that by multiplying by minus sign and redefining our function fi as minus fi, we can make it less than equal to form. So these are the 2 things that we keep in mind when we are writing a problem in standard form. Standard form is important because people assume that you have posed your problem in standard form when you are using their libraries, let us say. Okay. So consider the following. So these are the box constraint problem that we have solved last time, and in this case it splits into 2 sets of inequality. So li is less than equal to xi, and in this case is like ui is greater than equal to xi. So this this looks to be in the good form. So xi less than equal to ui, but the other one is not in good form. So we multiply by the minus here. So this will give us minus xi is less than equal to minus li. After changing this and rearranging the indices, we make this into standard form, and then problems with box constraints can be solved with some standard libraries. So this is the breakup that we have done. And one more thing was we have to bring these guys on the left because standard form doesn't allow any non-zero entity on the right hand side. So that's why we have done both this thing here. And then we can rearrange the indices and we can arrange these indices and say that is li minus xi and the remaining one starts from n plus 1 to 2n. Okay. And once you have this, then you can use the standard libraries. Okay. So sometimes you may be given a problem that doesn't look at first in the standard form, but with a little bit of tricks, you may always transform this into some standard form. It is not necessary to have equality constraints all the time, okay? Or it's also not necessary to have inequality. It could be either both, okay? And if it is not, if none of these inequality or equality constraints are there, then we call the problem a unconstrained problem. So we have like various scenario here, okay? So maximization problem, as I have said before, can be seen as a minimization problem. Okay, so if someone gives you a maximize f naught x, then it's easy to convert this into minimize by just changing f naught x to minus f naught x. You don't have to change the constraints. Okay, so this is the maximization problem is now changed to minimization problem, and it is in standard form. All other things are fine. So right hand side of the inequality and equality are 0, and there is only less than equal to inequality, and then this is fine. So by just changing this minus, we change this to minimize from maximize. So we don't have to need any additional library for maximize. We can solve it via the minimize library. Okay. And note that the constraints remain the same. You don't have to do minus on the constraints. Okay, that will be illegal. Okay, so you should not do this change of the sign of the constraints. The constraints remain the same. And obviously, like the optimal value in the case of maximize, instead of infimum, we do the supremum. Okay. So that's when the optimal value of for the maximization problem, you replace this by supremum, or you could have transformed this problem into another like we have known before, but you do minus f naught x. So this is the same thing as minus f naught x, and then the constraints less than equal to an equality constraints that you have to satisfy here. Okay, so these are just like basic terminology that I'm going through rather quickly. So two problems are equivalent if from a solution of the one, a solution of the other can be found. So someone may give me an optimization problem 1, and then I'm given optimization problem 2. So I say that they are equivalent if I can obtain one solution from the other. So obtain a solution of one from another. Okay. Okay, that's what is written here also. Okay, so then I say that these optimization problems are equivalent. So in other words, solving 1 is same as solving 2. Okay, or solving 2, I can do some transform after that and get back the solution of 1. So it's like can be obtained, right? I'm not saying that the solution is exactly equal. Okay, I'm not saying the solution is exactly equal. So maybe the solution here was x, and I may have to do some transformation, let us say 2x minus 3 or something like that to get a solution, optimal solution here. So the idea here is that I can get by doing this transform. Okay. Similarly, I may have some solution here and I can do some transformations and then I get for that I get the optimal value and optimal point there. Okay. So in the broad sense we are saying that they are optimal. Okay. So let us consider some examples. So consider the following problem, which is the minimization of alpha naught f naught x, and subject to alpha I fi is so this is the inequality constraint, and this is the equality constraint, and where alpha I is greater than 0 is given and beta I is not equal to 0 is given to us. Okay, so can I reduce this problem into a problem which is equivalent? Okay, so can I reduce this problem into problem where I get an equivalent formulation and the solution won't change? Okay. In other words, are these alpha I, beta I, and all these are like just there to confuse you, right? But do they really have a role to play? Okay, so that's the question here, right? So can I like simplify these things? Okay, so that's the question to play. Like in this case, like you have to be clear about the values that alpha I, beta I's have. So alpha I are given to be positive. So what does this tell us, okay, about this inequality? Can I simplify this inequality given that alpha I is positive? Okay, so alpha I fi x is less than equal to 0 is equivalent to, so can you tell me how can I simplify this further? So let us say this is alpha I is greater than 0, right? Yeah, so tell me quickly.
fx less than 0.
Yeah, so fix, yeah, so it's pretty standard. So fix is less than equal to 0, okay? And beta I is given to be non-zero. So, okay, so if you look at this equality, sorry, and beta I is non-zero. We know that if beta is non-zero, we can divide by beta I. So this is same thing as saying that hix is equal to 0. And I'm saying equality because I can also go back. I can multiply by beta I on both sides and doesn't change, right? And same thing happens here. If I multiply by some positive value scalar alpha I, the inequalities don't change. So they are like exactly like equivalent problem. Okay. And here alpha naught is also positive. Okay. So this means that minimizing alpha naught f naught x is same thing as minimizing f naught x. Okay, what will change is what is the change? So change is only the optimal point. I mean the optimal value. Okay, so optimal value will change. Optimal point remains the same. Optimal point remains same. Okay, so I'm just writing this so that you so there are problems where it's just some parameters maybe they're just to confuse you, but you very well know that this is actually these parameters actually could have been removed completely and without changing your optimal value. But then once you have found the the optimal point, okay, so once you have found the optimal point, to get the optimal value you have to multiply back alpha naught times. So if x star is optimal value, then p star is alpha naught f naught x star. Okay, so we do have to multiply this. Don't forget this. Don't forget. Okay, so although the optimal value have changed, but we could have reduced this problem into simpler problem by removing these. In fact, all these parameters could be removed without changing anything, and then solve it. Okay, so there are many examples we will see in this course where we simplify things to a point where it's much cleaner. Okay, so here alpha I can be removed from the inequality and beta I can be removed from the equality. That's what we derived. Minimizing alpha naught f naught x is same as minimizing f naught x. Hence, it is equivalent to the problem this. Okay, so we say that this and this problem are equivalent because a solution of the one can be used to find the solution of the other. In this case, it's a very specific case where x star is the same. So x star here and x star here are same. Okay, so that's a very particular case. But remember, definition of equivalent is a little bit more broad. So it does not have to be exactly same, but some transformation is there by which I can do some transform and then I can get here, or I can get here by doing some inverse transform. So equivalent means in a more broader sense, but in this case, it's like solutions are exactly the same. Okay. So equivalent problems, let us see what are the other cases that I'm talking about. So let us say there is some function phi which is from Rn to Rn and it is 1, 1. Okay, so remember 1, 1 functions, right? So is this function 1, 1? Can you tell me? So I do a quick check of 1, 1 functions. Okay, so is this so which of these is 1, 1? Can you tell me?
The B is 1.
Yeah, B. Okay, so only B is 1, 1. Only B is 1, 1. Only B is 1, 1 because 1, 1 means like for 1x there is 1y. That's it. Okay. I should cannot. I mean for 1x there is always 1y. That's the definition of function. But what I'm trying to say is like for 2x I should not have 1y. Okay, so for 2x I should not have 1y. So do we have it here? Okay, so if I look at this point, okay, So indeed for 2x, I have the same 1y. Okay, the height is the same, right? So that's not 1 1. Okay, so that these are the cases where, so here also we can draw a flat, and then we see that at many places, many different values of x, I have the same height. Okay, so these are not 1 1. So this is not 1 1. This is not 1. This is 1 1, and this is not 1 1. Okay, so this was just a quick check. So what this result is saying is like if you are if your function f, let us say if your function f is in some domain, let us say this is the z variable domain. Okay, so this is the variable where you are working with z, and let us say you did a transform of your z variable by some phi function, let us say this phi function, which is 1 1. Okay, and so this phi function, if you do a transform of this, then I go to a different space where my variables now look like phi z, right? So let us say I call this u. Okay, so I go from the z variable to u variable. I have transformed my problem by doing this. Okay, and then I apply fi on that. Okay, so let us say these are the inequality constraints and equality constraints. So what this is, what this result says here is that if you do this, provided that the phi is 1 1, so this is like 1 1 function, then the problem that you were solving here, okay, so the problem that you were solving here were minimize f naught and then subject to fi like less than equal to 0, hi equal to 0. And the new problem where, so this was the z variable problem. Now you are talking about minimize f naught of z. Okay, sorry, u. Okay, so u, and here you were talking about minimize f naught of z. Okay, so if you transform your problem in a way where you can identify the variable as phi of z, okay, where phi is 1 1, then the minimizations that you will obtain here will correspond to the minimization that you obtain here. Okay, or the optimal point will be the same. Okay, so that's what this result is saying. So the problem, so this is a minimization over let us say u, right? Because this is the new variable in the new world. Okay, and since we have done this transform, we can give this a tilde name, right? So this is like the tilde name, and then like fi tilde is less than equal to 0 and hi tilde equal to 0 and so on. I have not said about hi yet, right? So if I do a transformation of my z in a way that this is via some 1 1 map, then the resulting problems are equivalent. Okay, so this is the hint I gave you. Now let us look into the text. So this is fi, which has done a transformation via phi. Okay, so I took z and moved it to phi.